Hello 105 students. Ryan here to help you understand the fundamental quantitative lab skills experiment. Let's begin by going over what you'll get out of this experiment and why you're doing it. 1. It will help you understand what accuracy and precision are and the difference between them, which is something you'll need to know about when you go to analyze data in subsequent experiments. 2. It will introduce you to two different pieces of lab glassware, the pipette and the beaker, and teach you how to read them. And 3. It will help you evaluate the accuracy and precision of these two glassware pieces. Having some experience with these pieces will help you select the right glassware to measure stuff out with in later experiments. So what are accuracy and precision? What do these two terms mean? Well, accuracy refers to how close a measurement is to its actual or true value. For example, let's say you had two different 1-cup measuring cups and you used each one to measure out a cup of water. Let's also say you had some method to determine the exact amount of water you measured out with each cup. This method tells you that you measured out 0.92 cups with one of the measuring cups and 0.98 cups with the other. Since the second cup came closer to measuring out what its label claims it does, that cup is the more accurate of the two. Now let's go over precision. This word can actually mean two different things. In one sense, it's kind of synonymous with consistent and refers to the extent to which multiple measurements vary from each other. Going back to our measuring cup example, let's say you measured out 3 cups of water with each measuring cup instead of just one, and you determined the actual quantity of water you dispensed each time. The first cup actually gives you 0.92, 0.89, and 0.97 cups of water, while the second cup gives you 0.98, 0.97, and again 0.98 cups of water. You can see that the first cup's measurements vary a lot more from each other than the second cup's. In other words, the first cup's measurements are less consistent and therefore less precise. The other way to look at precision is as the number of significant figures your measuring tool gives you. To show you what I mean, let's look at these two scales. The scale on the left gives us readings to the nearest hundredths of a gram, while the scale on the right gives us readings to the nearest thousandths of a gram. Since we get an extra digit from the latter, we'd say its readings have more precision. In this experiment, you are going to compare the accuracy and precision of a beaker to that of a pipette. Of course, in order to do this, you'll need to know how to correctly use each piece. Of the two, the beaker is simpler, though there is something you'll need to know about in order to use it properly, and that something is interpolation. To show you how this works, I've got a graduated cylinder here with some water in it, and you can see the bottom of the meniscus, that's the curvy shape the top of the water takes, the bottom of the meniscus falls somewhere between the 27 and 28 milliliter marks. To read this properly, we will use our imagination to add an extra set of markings between the real ones that divide the space between the real markings into 10 segments. Since the real markings go up in increments of 1 milliliter, our imaginary ones will go up in increments of 0.1 milliliter. Now we just have to figure out which of these imaginary lines the meniscus's bottom lines up best with. In this case, it seems to line up best with the 27.5 mil marking, so we would read and record this as 27.5 mil. If you're trying to read a piece of glassware and you're not sure what you're supposed to interpolate to, just take the actual physical markings on the piece you're working with and divide by 10. This graduated cylinder's markings go up in increments of 2 milliliters, so you would read and record this one to the nearest 0.2 mil. If you're not used to doing this, it can sometimes be a little hard to figure out what the value of that last digit is, especially since the lines I put up on the example cylinder don't really exist. Just do the best you can, and don't worry too much if you read a little high or a little low. Interpolation is, after all, subject to interpretation. That's how you use graduated glassware. Now let's talk about the pipette. To use your pipette, you first use a pump to draw solution up to just past the pipette's index line. You then take the pump off and use your thumb or finger to hold the liquid up, then let it drain back down to the line. To dispense the liquid, hold the pipette over the container you need to get the liquid into and let it gravity drain. When it's done, touch the tip to the side of the container to get the last drop off. If you look close, you'll see a small bit of solution will get left behind in the pipette. It's calibrated to account for this, and this is why you don't want to use the pump to force the liquid out of it. You'll note that, unlike a beaker or a graduated cylinder, your pipette has no graduation marks to read. The amount of water you dispense with it is whatever it's rated to dispense, which is etched or painted somewhere on the pipette's side, along with its precision. So now that you know how to use the glassware pieces you'll be working with, let's go over what you'll be doing with them. You are going to use each piece to make a series of solutions of brilliant blue FCF dye, with each solution in the series made to a different concentration. You will then use one of these here fancy devices, a spectrophotometer, to measure how much light each solution absorbs. The more concentrated they are, the higher their absorbance will be. To show you what I mean, let's compare these two solutions. The one on the left is less concentrated, appears lighter and easier to see through, and has an absorbance of 0.1. By comparison, the one on the right is more concentrated, darker and harder to see through, and has an absorbance of 0.8. The take-home message is higher concentrations result in higher absorbances. For a separate video on using the spec you'll take your absorbance measurements with, see the link in the description. In your post lab, you will take your solution's absorbances and plot them on a graph versus their concentrations. When you do this, make sure to give your graph titles, tell Excel you want it to have a trend line, specifically a linear trend line, and that you want the equation for this line and something called an R-square value to appear on your chart. In a perfect world, with all your solutions made and measured perfectly, the data points on your graph would all line up in a perfectly straight line. However, in the real world, the glassware pieces you will be working with are not perfect, and as a result, your solution's concentrations won't necessarily be what you think they are. A solution you calculate to be 0.06 molar, for instance, might actually be 0.065 molar. Because of this, the points on your graph may or may not all fall in a straight line. The extent to which they do is reflected in the R-square value. The closer they lie to the best fit line, the closer R-squared will be to 1. You can see what I mean if you compare the graph on the left with the one on the right. The data points on the left graph deviate greatly from the line, and so this graph's R-square value, 0.9216, is kinda bad. The data points on the right graph, however, are close to the line, and so the right one has a pretty good R-square value of 0.9975. Since your plot's linearity, represented by R-squared, depends on how precisely you made your solutions, you can use it to evaluate your glassware. Glassware that cannot precisely measure out liquids will give you a series of solutions that vary a lot from what they should be, and this will show up as a low R-square value. Aside from evaluating the precision of your glassware, you will also evaluate its accuracy. To do this, you will measure the absorbance of a known solution, in other words a pre-made solution you already know the concentration of, and use your plot to determine its concentration for yourself. If, for example, your plot looked like this and your known's absorbance was 0.37, you'd put that down here on the y-axis, then come straight over to the best fit line, then go straight down, and see what concentration you got. In this case, the line goes to about 0.048, so this solution's calculated concentration is 0.048 molar. By comparing this number to the known's actual concentration, you can determine how accurate your plot is, and by extension how accurate your glassware pieces are. And that's what this experiment is all about. As always, make sure you dispose of all solutions in the lab room's waste container and thoroughly rinse your glassware when you're done.